Today, there are billions of devices, sensors, and controllers in homes and in factories, on farms, in hospitals, and in cars that can be connected together to create incredible applications. Be these simple systems that turn on a light bulb, or controllers that can adjust the output of a wind turbine, a flow monitor that can make adjustments on the fly in a manufacturing line, or a smart car that can report issues before they happen. How do we communicate with these devices? How do we link them together and create smart systems? How do we analyze the data from these devices? That is the focus of our class, IoT on AWS. In this class, we will build an IoT solution on AWS. You will have the opportunity to create an IoT application that uses several IoT services. You will use AWS IoT Software Development Kit to programmatically communicate with and control remote devices. We will look at a distributed architecture where we will tie in devices at the edge using AWS IoT Greengrass, and we will use AWS Analytics to collect data from our devices to make intelligent decisions about how to manage these devices. Throughout the class, there will be hands-on exercises that you can complete in your own AWS account. Now, you won't need any special hardware for this class. We will take advantage of the AWS cloud resources to simulate devices. Still, the lessons learned should directly transfer to actual IoT devices. Please join us for this exciting 4-week journey learning about AWS IoT. Today, there are billions of devices, sensors and controllers in homes and in factories, on farms and in hospitals and in cars that can be connected together to create incredible applications. Be these simple systems that turn on a light bulb, or a controller that can adjust the output of a wind turbine, a flow monitor that can make adjustments on the fly on a manufacturing line, or a smart car that can report issues before they happen. How do we communicate with these devices? How do we link them together and create smart systems? How do we analyze the data we collect? This is the focus of our class, IoT on AWS. My name is Alan Goldberg. I'm a Curriculum Development Manager with Amazon Web Services. I will be joined by several of my colleagues here at AWS as we discuss these topics, and we'll see where AWS solutions fit in the world of the Internet of Things. In this class, we will build an IoT solution on AWS. You will have the opportunity to create an IoT application that uses several IoT services. You will use the AWS IoT Software Development Kit to programmatically communicate with and control remote devices. You will look at a distributed architecture where we will tie in devices at the edge using AWS IoT Greengrass. We will use AWS Analytics to collect data and make intelligent decisions about how to manage these devices. Throughout the class, there will be hands-on exercises that you can complete in your own AWS account. Now, you won't need any special hardware for this class. We will take advantage of AWS cloud resources to simulate devices. Still, the lessons learned should directly transfer to real-world IoT applications. We will also have links to reference materials and readings, as well as some quizzes to help you gauge how you are understanding the concepts we present. Joining me for this course will be Bobby, Adam, Neil, and Wes. Next, we will have a brief introduction to our team, and then Wes will get us started with an introduction to IoT. Have fun. I look forward to visiting with you throughout the next 4 weeks of our class.
Welcome back. I'm Wes, and I'll be doing a quick overview of just what AWS IoT is all about. At AWS, we start our customer engagements for IoT with one simple question. What if you could know the state of everything and you could reason on top of that data? What problems would you solve? And we make it our mission to make sure that you can know the state of everything, of all your devices, and you can reason on top of that data so that you can truly solve your business problems. Today, there are billions of devices in homes, factories, oil wells, hospitals, cars, and thousands of other places. With the proliferation of devices, you increasingly need solutions to connect them and collect, store, and analyze device data. AWS IoT is a platform that provides secure, bidirectional communication between internet-connected devices such as sensors, actuators, embedded microcontrollers, or smart appliances, and the AWS cloud. This enables you to collect telemetry data from multiple devices and store and analyze that data. You can also create applications that enable your users to control these devices remotely from their phones or tablets. It provides a deep, broad functionality spanning from the edge to the cloud, so you can build IoT solutions for virtually any use case across a wide range of devices. Since it integrates with AI services, you can make devices smarter, even without internet connectivity. Built on the AWS cloud, used by millions of customers in 190 countries, AWS IoT can easily scale as your device fleet grows and your business requirements evolve. We also offer the most comprehensive security features so you can create preventive security policies and respond immediately to potential security issues. So why would you want to use AWS IoT? AWS has broad and deep IoT services from the edge to the cloud. Additionally, device software like Amazon FreeRTOS and AWS IoT Greengrass provide local data collection and analysis at the edge, even without internet connectivity. AWS is the only cloud provider to bring together data management and rich analytics and easy-to-use services designed specifically for noisy IoT data. AWS offers services for all layers of security. It includes preventative security mechanisms such as encryption and access control to device data. It also offers a service to continuously monitor and audit security configurations. You receive alerts so you can mitigate potential issues, such as pushing a security fix to a device. AWS is bringing AI and IoT together to make devices more intelligent. You can create models in the cloud and then deploy them to devices where they run 2 times faster compared to other offerings. AWS IoT sends data back to the cloud for continuous improvement of models. It also supports more machine learning frameworks compared to other offerings. AWS IoT is built on a scalable, secure, and proven cloud infrastructure and scales to billions of different devices and trillions of messages. It integrates with services such as AWS Lambda, Amazon S3, and Amazon SageMaker, so you can build complete solutions such as an application that uses AWS IoT to manage cameras and Amazon Kinesis data streams. In the next module, we will discuss in more detail just how all this IoT stuff works on AWS and show you how you can know the state of everything and how to reason on top of that data to solve real-world business problems.
Hi, Adam here. This module covers AWS IoT Core, which is a managed service that allows connected devices like cars, lights, smart speakers, cameras, fans, and really any other item you'd like to connect to easily and securely interact with cloud applications and other devices. AWS IoT Core can support billions of devices and trillions of messages, and can process and route those messages to AWS endpoints and to other devices reliably and securely. Your applications can keep track of and communicate with all your devices, all of the time, even when they aren't connected. You can interact using the AWS Management Console, AWS SDKs, AWS CLI, and the AWS IoT Core APIs. Connected devices can use the AWS IoT Device SDKs to simplify the communication with the AWS IoT Core. Okay, let's get into the first portion of IoT Core now, starting with the device gateway. The device gateway supports the pub-sub messaging pattern, which enables scalable, low latency, and low overhead communication. It is particularly useful for IoT scenarios where billions of devices are expected to communicate frequently and with minimal delay. PubSub involves clients publishing messages on logical communication channels called topics, and clients subscribing to topics to receive messages. The device gateway enables the communication between publishers and subscribers. Now, traditionally, organizations had to provision, operate, scale, and maintain their own servers as device gateways to take advantage of PubSub. AWS IoT Core has eliminated this barrier by providing the device gateway. The device gateway scales automatically with your usage, without any operational overhead for you. AWS IoT Core supports secure communication with the device gateway, AWS account level isolation, as well as fine-grained authorization within the AWS account. The device gateway currently supports publish and subscribe over secure MQTT and WebSockets, as well as publish over HTTPS. Next, I would like to discuss the message broker. It is a high-throughput PubSub message broker that securely transmits messages to and from all of your IoT devices and applications with low latency. The flexible nature of the message broker's topic structure allows you to send messages to or receive messages from as many devices as you would like. It supports messaging patterns ranging from one-to-one, command-control messaging, like my drawing here at the top of the screen, to 1 million or more broadcast notification systems, and really everything in between. In addition, you can set up fine-grained access controls that enable you to manage the permissions of individual connections at the topic level, ensuring that your devices and applications will only send and receive the data that you want them to. This is particularly helpful in my second example. We don't want all the cars to be able to broadcast an emergency, just those with the proper authority. The message broker is a fully managed service, so no matter how you choose to use it, it will scale automatically with your message volume without requiring you to run any infrastructure. It's a beautiful thing. Security for end-to-end IoT message structure is very important, given that IoT has many diverse and potentially sensitive information use cases. AWS IoT Core provides authentication and end-to-end encryption throughout all points of connection, so that unencrypted data is never exchanged between devices and the AWS IoT Core without a proven identity. In addition, you can preserve secure access to your devices and applications by applying policies with granular permissions. Also important for proper IoT deployment is a feature called Device Shadow, which enables cloud and mobile applications to query data sent from the devices and send commands to devices using a simple REST API. More detail on both of those areas in a later video. I have a question. Do you have a problem with a part on your car that keeps failing? Wouldn't it be nice if you were able to filter, transform, and act on the data provided to you, make your changes, and then verify the corrections were sufficient using that data in real time? Well, with AWS IoT Core Rules Engine, you can filter, transform, and act upon device data on the fly, based on business rules that you define. You can update your rules to implement new device and application features at any time. AWS IoT Core makes it easy to use AWS services like AWS Lambda, Amazon Kinesis, Amazon S3, Amazon DynamoDB, Amazon CloudWatch, and Amazon Elasticsearch Service for even more powerful IoT applications. IoT Core has another major area which I believe is deserving of its own video. That's the registry. Stay tuned into this course, and I'll see you in an upcoming video to explain why the registry of IoT Core is so important to you.
Hello builders, what's up? Neil here. Welcome to this video. Now that you know about the different IoT services on AWS at a high level, let me introduce you to what you are going to build in this course. Ready? Hold your breath. You are going to build a connected vehicle solution. Is it not a fun project? We thought so. When we think of connected vehicle technologies, we often think about self-driving cars or autonomous vehicles. But there is more to it. Did you know all cars and light trucks built and sold in the United States after January 1st, 1996 had onboard diagnostic ports, also referred to as OBD2 ports. And if you have a connector to that port, you can collect a wealth of information on vehicle status and activities such as windshield wiper status, traction control status, headlight status, airbag deployment status. It's very similar to how you transfer your data using USB connectors from one machine to another. And that's why cars are the new data center on wheels. To date, with an OBD2 connector, you can physically collect this data to analyze it. Here's the twist. Connected vehicle technology aims at getting all this data bypassing the physical data transfer limits. And the way they do it is by taking advantage of cloud and IoT. And thus, there is a need for a new hardware and software combo for this kind of communication that goes in the cars. And it's becoming an industry standard, with many automakers already working on implementing this. Connected vehicle technology comes in different flavors. I will focus here on the three main ones. The first one is vehicle to vehicle, where the vehicles can communicate to each other on the road. Self-driving vehicles or any connected vehicle is a great example of this. They can collaborate with other vehicles in real time to avoid collisions or reducing accidents. The second flavor is V2I, or vehicle to infrastructure communication. In this mode, messages can be broadcasted out to the cloud directly or via roadside hardware towers, which will be pretty common in smart cities, to the cloud. And these messages can then be enriched with various other data sources like weather management systems or traffic management systems. Do you ever sit in your car at a stoplight wondering if it will ever turn green? I do. Many cars today are equipped to receive real-time signal information from citywide traffic management systems. And that's one of the problems that V2I communication can help with. The third flavor is I2V communication, or infrastructure to vehicle communication. Vehicles can get the data back from the cloud. Because remember, data adds more value when it sits adjacent to other data. And cloud, using its immense horsepower, can process petabytes and zettabytes of data and then predict the road conditions or other situational events in real time and send the messages back to the vehicles. Thus, you can imagine intelligent transportation solutions using connected vehicle technology will improve traffic, reduce accidents, and even reduce the energy carbon footprint. And in this course, you are going to create some simulated cars that will reflect all these different scenarios. And no points for guessing, you will use the AWS IoT suite of services to accomplish that. Sounds exciting? Let's make it happen. Thank you for listening to me. See you soon.
Hi there and welcome. In this video, we are going to talk about registry, which is a component of IoT Core. A very important component, that is. Registry establishes an identity for devices and tracks metadata such as the device's attributes and capabilities. The registry assigns a unique identity to each device that's consistently formatted, regardless of the type of device or how it connects. It also supports metadata that describes the capabilities of a device. For example, whether a sensor reports temperature, and if the data reported is in Fahrenheit or Celsius. The registry lets you store metadata about your devices, and metadata in the registry does not expire as long as you access or update your registry entry at least once every 7 years. That's particularly useful for IoT devices that make connection requests and pass information only when an event triggers them. Now that event could be annually or every 2 years or 3 years or 4. As an example, a sensor that determines when a crop is mature and ready for harvest. Typically that type of signal would be sent once a year, maybe twice. Also important would be the knowledge year over year of any changes in maturity rate. The benefit here is that you would not have to register the devices over and over again. Also, the data would be formatted consistently. if you procure a new device. So that's pretty cool, huh? At this point, you're probably realizing that registry is a first stop for configuring and connecting your device to IoT Core. The process of registering a device takes 4 major steps. First, you will register your device, which is very simple to do since there's a wizard that walks you through the steps. One additional option I would like to point out to you is that you can register one device or many devices at once. Just choose based on your workload with IoT. Next, you will need to add an X509 certificate and key pair. I would like to also point out here that you can bring your own certificate or create a certificate based on a private key that you own. In this step, you will create the certificate and key pair, and then associate it to the IoT device, and then activate the certificate. Also, I want you to take notice that you are allowed to skip this step, but it is only for the time being. No matter what, you will have to have a certificate before you're able to connect the device. Almost there. We will now define a policy for our thing. Policies are important. Policies determine what an authenticated identity can do. An authenticated identity is used by devices, mobile applications, web applications, and desktop applications. An authenticated identity can even be a user typing on AWS IoT CLI commands. The identity can execute AWS IoT operations only if it has a policy that grants it permission. Once the policy is defined and saved, the last step will be associating the certificate to the thing, which is really quite simple since the entries from the previous steps appear as a selection in this area. Those steps make the connection process very simple and secure. One quick pro tip for your deployment: make sure that you're not including PII or sensitive information in the naming of your policies or devices. I hope you find the information provided in this video helpful as you create your first thing.
What's up, builders? Welcome back. Earlier, I told you about the project. In this video, I'll show you the architecture that you will be building throughout the course. So, you will start with 2 fancy cars. You will download the codes and you will start to push telemetry data from these cars to AWS IoT Core. Once you are happy with it, you will move on to another exercise where you will play with the shadow capability of the cars. And then you will also build a static website which will use cognitive identities to talk to the AWS IoT Core, and you will be able to change the settings of the car. And then we'll introduce you to Greengrass, the local edge computing part, which is super exciting, where you will configure all the different subscriptions so the cars can talk to each other and also to the cloud. We'll also show you how you can get your local compute at the edge that I had been telling you about. And that's where you will deploy Lambda functions on the edge to push the telemetry data to IoT Core as well. And now, once you are getting all the data, you are not just doing that for fun, right? You want to analyze all this data to generate meaningful insight for your business outcomes. So you will use AWS IoT Analytics and its different components to collect the data, process the data, store the data, and finally analyze the data using SQL datasets to generate meaningful outcomes. Sounds like fun? Let's go build. What's up? The first exercise of this course is up. In this exercise, you will provision 2 cars, car 1 and car 2, which will act as IoT things. These cars will be pushing telemetry data like oil temperature, engine speed, latitude, longitude, and many other data points to AWS IoT Core service in the cloud, which you can view. How will you do this? You will first launch a Cloud9 environment. This will be your sandbox for the course. Then you will create the first car via the AWS IoT console. And that process includes creating an IoT thing, a certificate for MQTT-based authentication, and a policy which will define what permissions your car has once authenticated. You will create the second car via AWS CLI commands. Since you are builders, we wanted you to explore both the options. Once the cards are created, you need to take a ride, yeah? So to start the car engine, you will download some Node.js code and run it. Finally, you will use the MQTT test client built into the AWS IoT console to subscribe to a topic to view the messages coming from the cars. And when you are done with the exercise, do not forget to stop the Cloud9 environment to avoid any additional cost. Sounds good? Oh, you have a question. You are thinking, in the real world, how is this going to work? In the real world, cars will be equipped with hardware and software with similar code, and they will be able to talk to AWS IoT Core endpoints to publish or subscribe similar messages. Sounds good? Let's do it, builders. See you soon.
Welcome to week 2 of IoT on AWS. Last week, we introduced AWS IoT services. Specifically, we talked about the IoT core services, and you built an application that collected data from a car and integrated that data with IoT. This week, we'll dive a bit deeper into the AWS IoT. To start, Bobby will explain how IoT rules work. Rules give your devices the ability to interact with other AWS services. You will then get to do an exercise where you will apply IoT rules to the telemetry data sent by your car. Bobby will then dive into the AWS IoT Shadow. The Shadow is a very cool concept. It allows you to see the last known state of a device and lets you set a desired state for your device if it is online or when it becomes available. You will then do a lab where you interact with the device Shadow using both AWS Command Line Interface, or CLI, as well as the AWS console. This is a big week, and after working with rules in Shadow, Wes will discuss and demonstrate how to use the AWS IoT APIs and SDKs to programmatically interact with the AWS IoT services. You will follow this up with an exercise where you will use the SDKs and APIs to build out your IoT app to send messages between cars. Like in week 1, there'll be some course notes and a quiz so you can gauge how much you've learned. As in the first week, if you have any questions or want to help out your fellow students, feel free to jump into the forums. We as well will be paying attention. So now, I'll pass this off to Bobby to get you started in week 2.
Hi everyone, Bobby here. We're going to talk about AWS IoT rules. Rules give your devices the ability to interact with AWS services. Rules are analyzed and actions are performed based on the MQTT topic stream. MQTT is a machine-to-machine connectivity protocol based upon a publish and subscribe model. It was designed to be extremely lightweight. It is useful for connections with remote locations where a small code footprint is required and/or network bandwidth is constrained. For example, it has been used in sensors communicating to a broker via satellite link, over dial-up connections with healthcare providers, and in a range of home automation and small device scenarios. You can use rules to support tasks like these: augment or filter data received from a device, write that data received from a device to an Amazon DynamoDB database, save a file to Amazon S3, send a push notification to all users using Amazon SNS, and much more. Your rules can use MQTT messages that pass through the publish-subscribe message broker for AWS IoT, or using the basic ingest feature, you can securely send device data to AWS services without incurring messaging costs. The basic ingest feature optimizes data flow by removing the publish-subscribe message broker from the ingestion path, so it's more cost-effective while keeping the security and data processing features of AWS IoT. Before AWS IoT can perform these actions, you must grant permission to access your AWS resources on your behalf. When these actions are performed, you incur the standard charges for the AWS services you use. An AWS IoT rule consists of a SQL select statement, a topic filter, and a rule action. Devices send information to AWS IoT by publishing messages to the MQTT topics. The SQL statement allows you to extract from an incoming message. The topic filter of an AWS IoT rule specifies one or more MQTT topics. The rule is triggered when a message is received on a topic that matches that topic filter. Rule actions allow you to take the information extracted from the message and send it to another AWS service. Rule actions are defined for AWS services such as Amazon DynamoDB, AWS Lambda, Amazon SNS, and Amazon S3. By using a Lambda rule, you can call other AWS or third-party web services. See this week's notes for the URL and other information related to actions that you can take using AWS IoT rules. Here are some helpful hints for troubleshooting errors. The AWS IoT rules engine may make multiple attempts to perform an action in case of intermittent errors. If all attempts fail, the message will be discarded and the error will be available in your CloudWatch logs. If an error action is defined in the rule, it will be invoked after that failure. If you're having an issue with your rules, you should enable Amazon CloudWatch logs, the AWS monitoring service. By analyzing your logs, you can determine whether the issue is authorization or whether, for example, a where clause condition did not match. You're going to have an opportunity to investigate IoT rules in the upcoming lab.
What's up? Welcome back, builders. It's time for the next exercise. In this exercise, you will create a trigger that sends you an email notification when the fuel level of your car is lower than 25%. How will you do this? You will create a topic using simple notification service and subscribe to that topic via your email. Please ensure you have access to the email you are using, since you need to confirm the subscription for this entire workflow to work. Once you are done, you will add permission for the AWS IoT service to publish a notification to that SNS topic. And finally, you will create an IoT rule that looks for the fuel level using a SQL query on the incoming telemetry data, like the engine speed, like the odometer readings, and a lot of other things that you will get prior to publishing to that topic. So you will test this workflow by starting your car engine again. And voila, you should receive a mail within few minutes as the simulated fuel level goes below 25%. And again, do not forget to park your car. Oops, clean up once you're done with the exercise. Let's do it, builders. See you soon.
Hi everyone, this is Bobby back again, and now I'm going to talk to you about IoT device shadows. A device shadow is a JSON document or JavaScript notation doc that is used to store and retrieve current state information for a device. The device shadow service maintains a shadow for each device you connect to AWS IoT. You can use the shadow to get and set the state of a device over MQTT or HTTP, regardless of whether the device is connected to the internet. Each device's shadow is uniquely identified by the name of the corresponding thing. AWS IoT provides 3 methods for working with the device's shadow: update, get, and delete. An update method creates a device's shadow if it doesn't exist or updates the contents of a device's shadow with the data provided in the request. The data is stored with a timestamp information to indicate when it was last updated. Messages are sent to all subscribers with the difference between the desired or reported state. This is known as the delta. Things or apps that receive a message can perform an action based on the difference between desired or reported states. Let's say I can use a smartphone app to control the thermostat for my home. I have set the desired state to 72 degrees Fahrenheit. This is stored in my thermostat's shadow file. My husband, however, likes it cooler inside the house. When my husband gets home and looks at the app on his phone, the device is pulling the current temperature from the shadow file to report to him that I have it set to 72 degrees. He can choose to lower the thermostat to 65 degrees. This creates a change, or a delta, between the shadow files. The get method retrieves the latest state stored in the device's shadow, in this case my desired state of 72. The delete method deletes a device's shadow, including all of its contents. This removes the JSON document from the data store. You can't restore a device's shadow that you've deleted, but you can create a new shadow with the same name. The supported protocols for updating a device's shadow are supported through both MQTT and a RESTful API over HTTPS. Because MQTT is a publish and subscribe communication model, AWS IoT implements a set of reserved topics. Things or applications subscribe to these topics before publishing on a request topic in order to implement a requested response behavior. So how did my thermostat get updated? When my husband sent his request to lower the thermostat to 65 degrees, his app used the update thing shadow RESTful API. Or it could have used a publish or update topic. That's how my thermostat thing knew to take action, by lowering the thermostat. When you use the update thing shadow, only the fields specified in the request get the update. You can also retrieve a shadow document. If my app needed to retrieve my thermostat shadow, it would use the get thing shadow RESTful API or subscribe or publish to the get topic. This retrieves the entire document plus the delta between the desired and reported states. How does my thermostat know something has changed and it needs to lower the thermostat? It receives a notification from published messages on one of two MQTT topics. And these are reserved topics. They are AWS/things/thermostat1 in this case, or the name of your thing, /shadow/update/accepted, or instead of accepted, it's /delta. The message sent to the update delta topic is intended for the thing whose state is being updated. This message contains only the differences between the desired and reported sections of the device's shadow document. Upon receiving this message, the device, or thermostat in this case, should decide whether to make the requested change. If the device's state is changed, it's going to publish its new current state. So when my thermostat goes from 72 to 65 degrees, it's going to publish its new state on the AWS/thing/thermostat/shadow/update topic. Devices and applications can subscribe to either of these topics to be notified when the state of the document is changed. In an upcoming module, we will demo how to use shadows.
What's up, builders? Hope you're enjoying the exercises so far. In this exercise, you will interact with the shadow capability of AWS IoT Core. Do you have a car which lets you remotely lock or unlock the doors or turn off the lights from a mobile or web application? You do? I see some of you shaking your head. But do you know how it's generally done? Let me explain this in a little more depth, since shadows are generally misunderstood. The car, which is a real thing on the road, has a virtual representation, aka shadow, in the cloud to store its state. And it's easy to write applications to interact with your devices through device shadows rather than to the direct car. Because guess what? Your car may not be connected all the time to the internet. And if it's not, your commands to change the status of the lights or unlock the doors may get lost, and the car would never get the instructions. Also, being connected at all time is not energy efficient. Thus, the shadow can store the commands from your application, your mobile app or the web app, and whenever the car gets connected, it reads the latest instruction from the shadow, which is its digital representation, and flips the state. So, how are you going to do this? You will continue to use the Cloud9 environment. You will download some new code for the car and start the engine. Oops, the script. Then you will use the AWS IoT Core console to publish a new state for the car shadow to turn its lights on and off. Then you will stop the car engine to see what happens when you try to turn off the lights when the car is disconnected. I won't tell you what will happen, you will figure it out. In summary, you will learn about the shadow service within AWS IoT Core and different MQTT messages associated with it. And finally, don't forget to clean up once you are done with the exercise. Let's do it, builders. See you soon.
Welcome back. I'm Wes, and in this section, we're going to take a look at the code you've been using in the exercises so far and break it down. Additionally, we'll show you specifically how to use the AWS IoT SDK, for JavaScript in this case, to connect to your device and push messages through the AWS IoT Core service. So let's get started. So here we are logged into the AWS Cloud9 Integrated Development Environment, or IDE. For those of you who might not be familiar with AWS Cloud9, it is a browser-based IDE that you can use to work on your code. It's a pretty cool tool, got a lot of neat features. We're opening up our project. For those of you who've been following along at home and doing your exercises, you're already familiar with this project code. And we're going to open up this device example JavaScript file. As we scroll down and take a look at this code here, cracked up under the hood, we start out by creating a couple of constants, a couple of variables, or app dependencies. We define this first function for process test, and that's what's going to export that MQTT instance and connect to the AWS IoT endpoint. And by the way, the IoT endpoint, if we go back to the AWS IoT console, you'll see the card that you created earlier in the previous exercise. Back in our code, we slide down. We've got some other constants here, like the keys that we've used, some other variables for timeout. The real deal here is around line 51, where we create our test mode. And we're going to create basically two topics that we're going to publish, and that is going to create two devices. Those are basically virtualized cars or versions of our car that we created earlier. So we're going to have two versions. Test mode 1 is going to create topic 1. Test mode 2 is going to create topic 2. And those devices are simply going to pass messages back and forth between one another and communicate. And that's what we're going to try to verify. This last little section down here just logs all that traffic so that we have a record of what happened, where, who did what, when. And the last part is our endpoint. So let's fire this app up, shall we? We're going to start this out by opening up a new terminal window. We're going to get over to our project directory. And we're going to fire up our code. In this case, one thing to remember here is that we're going to use that endpoint. The test mode is going to be 1, so that's going to create topic 1. Now, that particular device has been fired up, and you see the connect there is pausing to connect because right now it has nothing to connect with. So we've got to create another device. So open another terminal window, change to our project directory, and we'll execute and fire up a second device. Make sure we change our little test mode not to 1, but in this case we're going to change it to 2 and fire that bad boy up. And now pretty quickly you'll see that messages are flowing. If I make these big for you, you can see that messages are in fact flowing between the two topics. Now, one way to verify that it's actually utilizing the IoT service is to go back to the console and click on the Monitor tab. And here you're going to see the number of successful connections that are being flung around, which is about 23 so far. You'll note that we're all using the MQTT protocol, pretty much 100%. You'll see the total number of messages published. It's pretty straightforward. If we want to test out this topic, we could also go into the client itself and we could subscribe to that topic. And again, we can see the messages flowing. It's really that simple. You can also pull down this project, if you have not done it in the past, at our GitHub repo. And we'll leave the links in the liner notes through our GitHub repo. Everything you need to execute this project and execute this exercise is located in the repo. So remember, all the documentation for this code is in the repo, so be sure to check it out. Plan to spend ample time looking at the SDK to get a good feel for it. It's been grand spending time with you on this discussion on SDKs. I'm Wes, and I'll catch you in an upcoming segment.
What's up, builders? Welcome back. I had been telling you the use case where the cars can avoid crash if they talk to each other in real time. And guess what? You are going to do that now. How? You already have created 2 cars in the previous exercises. Please ensure they still exist. If not, go back and redo exercise 1.1. You will continue to use the Cloud9 environment. You will download some new code for the cars to talk to each other over 2 different MQTT topics assigned to each car. Then you need to start driving your cars. So you will start the scripts in 2 adjacent Cloud9 terminals. And what you will notice is pure magic. Cars are talking to each other. We have also created a to-do section for you to try running your own code. But if you struggle, no worries. We have you covered with the solution too. Enjoy the drive. And don't forget to put on the brakes. Oops, you know what I mean. Do the cleanup once you're done with the exercise. You got this, builders. See you soon.
Welcome to week 3 of IoT on AWS. Last week, Bobby introduced the concept of IoT rules and the IoT shadow, and Wes explained how to use the AWS IoT SDKs. This week, we are going to look at some underlying concepts and features of our IoT service. Specifically, we are going to look at communications and security. We will then shift direction, looking at moving compute and IoT to the edge. Wes will kick us off by discussing communications with IoT. He will talk about the MQTT protocol as well as interacting with AWS IoT over HTTP and WebSockets. Bobby will then return to talk about security. She will review certificates and encryption. We will then have an opportunity to apply some of these concepts in an exercise where you will interact with the IoT shadow in your application, taking advantage of AWS IAM and Amazon Cognito to provide authenticated access to your application and data. We will next look at computing at the edge, moving processing closer to the device and using AWS IoT Greengrass to allow us to interact with devices that are not directly connected to the cloud. You will follow this up with an exercise adding Greengrass functionality to your application. And yes, like in prior weeks, there will be some course notes and a quiz so you can gauge how much you have learned. As in earlier weeks, if you have questions or want to help out your fellow students, feel free to jump into the forums. And again, we will be paying attention and listening. Now it's Wes's turn to start this week. Have fun.
Hello, my IoT friends. Welcome to the MQTT HTTP WebSockets video. In this video, we'll discuss the supported protocols of the AWS IoT Message Broker. Just a quick reminder on the AWS IoT Message Broker, it's a publish, subscribe service for sending and receiving messages to and from AWS IoT. When communicating with AWS IoT, a client sends a message addressed to a topic. The message broker, in turn, sends the message to all the clients that have registered to receive messages for that topic. The act of sending the message is referred to as publishing, and the act of registering to receive messages for a topic filter is referred to as subscribing. Also, before I describe the protocols, there's another thing worth mentioning. The topic namespace is isolated for each AWS account and region. For example, the sensor car1 speed topic for an AWS account is independent from the sensor car1 speed topic for another AWS account. And this is true of regions as well. The sensor car1 speed topic in the same AWS account in US East 1 region is independent from the same topic in the US East 2 region. And as of the production of this video, AWS IoT does not support sending and receiving messages across AWS accounts or regions. The message broker supports the use of the MQTT protocol to publish and subscribe and the HTTP protocol to publish. Both protocols are supported through IP version 4 and IP version 6. The message broker also supports MQTT over the WebSocket protocol. MQTT is a widely adopted lightweight messaging protocol designed for constrained devices. The message broker supports client connecting with the HTTP protocol using a REST API. Clients can publish by sending a post message to the endpoint and URL of your thing. If you'd like to use the HTTP protocol, you can find the endpoint for a thing in the AWS IoT console. AWS IoT supports MQTT over web proxies. A WebSocket connection is initiated on a client by sending an HTTP GET request. The URL used will be in the following form. When the server responds, the client sends an upgrade request to indicate to the server it will communicate using the WebSocket protocol. After the server acknowledges the upgrade request, all communication is performed using the WebSocket protocol. The WebSocket implementation you use acts as a transport protocol. The data you send over the WebSocket protocol are MQTT messages. A quick pro tip for you, we recommend using the AWS IoT device SDKs to connect your device to the AWS IoT when making a WebSocket connection. AWS IoT device SDKs support multiple popular programming languages. See the course notes for details. Thanks for joining me in this discussion of MQTT supported protocols. I hope you enjoy the rest of the course.
Hi everyone, it's Bobby, and we're going to talk about security in IoT. When someone presses an AWS IoT button, like a dash button, to order coffee, for instance, it's important to know who they are. This is obviously important as you will need to know where to deliver their coffee, but you also want to make sure they are a genuine customer. In much the same way as existing online customers identify themselves with a username, each AWS IoT button needs its very own identity. In AWS IoT, for devices using MQTT to communicate, this is done with an X509 certificate. In cryptography, X509 is a standard defining the format of public key certificates. X509 certs are used in many internet protocols, including TLS or SSL, which is the basis for HTTPS, the secure protocol for browsing the web. First of all, let's see how symmetric cryptography works. If I have a box with a lock, and I have a key for this box, the key is the only way to unlock the box. If I want to keep something safe, like my passport, I place my passport into the lockbox and I lock it. This protects it because I'm the only one with the key. It requires my key or a copy of my key to open the box and retrieve my passport. This is an example of symmetric cryptography. You can have one key and you can use it to encrypt or lock and decrypt or unlock your data. Now let's see how asymmetric or public key cryptography works. Let's say I need my husband to send my passport while I'm in Seattle. I'm in Seattle, but my passport's in Virginia. He needs to ship it to me in a locked box. He puts my passport in his lockbox and he locks the box with lock A. He will keep the key for lock A with him. He sends the box via a courier to me. It's locked and he has the key. I can't unlock it because I don't have his key. So I lock it with my key. We'll call this lock B. I now send the box back to Virginia, now locked with my lock, lock B, and it's still locked with my husband's lock, lock A. The box currently has two locks, and the courier company can't open them. The box reaches my husband, and he removes lock A. The box is still locked because I locked it with my key. Now my husband sends the box with my passport back to Seattle, only locked with lock B. When I receive the box in Seattle, I can now unlock it because I have the key for lock B. It's important to note that during this time, the back and forth, the courier was never able to access my passport. It was secure. It was protected. This is an example of how asymmetric cryptography works. We'll go into this concept further in an upcoming module.
What's up, builders? Hope you are enjoying the sessions from this week. Up until now, you have only learned and used MQTT protocol to interact with AWS IoT core endpoint from your devices. Surprise! We support other protocols too, like HTTPS and WebSockets. Why? Because customers like you asked for it. By now, you know IoT things need certificates and keys to communicate securely to the cloud. But what if your IoT things are not hardware devices. It's mobile client or web applications. Are you going to hardcode the certificate and the keys in your code for millions of users? No! And that's where Cognito Identity plays a key role. Amazon Cognito is a service that lets you add users sign up, sign in, and access control to your web and mobile applications. Cognito Identity is a feature within that service that lets you create unique identities for your users from the mobile or web application and authenticate them for secure access to AWS resources like AWS IoT Core, S3, and others. So the next question is, how do you build this? You will start with creating a Cognito identity pool. When doing so, you will create different IAM roles with required policies that will allow the role to communicate with the thing shadow of car 1 or car 2. We'll give you some code samples and assets to host a static website on Amazon S3. The website will communicate with your Cognito identity pool to get the temporary credentials to authenticate to AWS IoT endpoint. And once the website is ready, it's hosted, you will start the car engine from the Cloud9 terminal, similar to before. You will browse to the website you created. You will interact with the car's shadow, which will flip the lights of the car. Tick-tock, tick-tock, tick-tock. Don't get lost in the shadow. And remember to clean up the resources once you are done with the exercise. See you soon.
Hi everyone, Bobby here again. Now we're going to talk about edge computing. And to understand edge computing, we're going to take a little trip back in time and discuss the history of computing. If we go way back to the 1950s, or as I call it, the beginning, there was just a mainframe. And then in the 60s, we had dumb terminals that we could connect to the mainframe. In the 1980s and 90s, we had personal computers. And this was the first time regular folks had a computer inside their home. In the 2000s, smartphones, tablets, and other devices came onto the scene. Now, and for the past decade, we are in the cloud computing era. We still have our personal computers, but we are using them to access centralized services like Amazon Prime Video and others. Additionally, devices like Amazon's Echo, Amazon Fire Stick, and other streaming services are powered by content and intelligence that's in the cloud. As opposed to the DVD of It's a Wonderful Life by Frank Capra, which I can now stream it anywhere using my Fire Stick from the cloud. So what is the edge? The word edge in this context means literal geographic distribution. Edge computing is computing that's done at or near the source of the data, instead of relying on the cloud to do all the work. It doesn't mean the cloud will disappear. It means the cloud is coming to you. AWS Greengrass is a great example of edge computing. Greengrass allows local execution of AWS Lambda, messaging, device shadows, and security. IoT Greengrass Core interacts directly with the cloud and works locally, even with intermittent connectivity. You'll be able to experience edge computing with an upcoming AWS Greengrass exercise.
Hello builders, what's up? This is Neil again. Welcome back. Earlier, we explained what edge computing is all about. In this video, I will explain the why and how of edge computing. I hope by now you are in love with the connected vehicle project. So let's get started. Think of a scenario when two self-driving cars are going to crash. Raise your hand if you think the car should wait for instructions from the cloud to avoid this crash. If you did raise your hand, I love your optimism, but honestly, no one has figured out yet how to beat the speed of light. Because if cars go to the cloud to get the response back, there is a round-trip latency. This is a law of physics. And cars in a crash-like situation cannot afford that. So, to avoid this crash, The cars, aka the edge device here, need to have local intelligence. How do they get local intelligence? It's possible with local compute and local machine learning capabilities, and they can work even with limited or no connectivity to the cloud. And that's just one example of edge computing. So the next obvious question is, hey Neil, does AWS have an edge computing service then? Yes, we do. And we have two of them. One is Amazon FreeRTOS, and the other one is AWS IoT Greengrass. Sounds like fun? Let's dive deeper. Amazon FreeRTOS is an operating system for microcontrollers that operates on the edge. So think of resource-constrained devices such as fitness trackers, pacemakers, toothbrush, and it needs only over 64 KB of RAM to operate because these are pretty small embedded devices. On the other hand, AWS IoT Greengrass is a software for edge devices or gateways with more horsepower and possesses many capabilities similar to AWS IoT Core. Let's quickly go over some of the features of AWS IoT Greengrass. The first one is local actions. You can run local Lambda functions on the edge. You also get a local message broker similar to AWS IoT Core in the cloud, so Greengrass can work completely in offline mode. You also have local device shadows to store the information of the state of all the devices at the edge. Everything we do starts with security. It's our top priority. So you get the same level of security that you get in the cloud at the edge too. You get the machine learning inferencing capability. So if the car is going to crash, it can do the inference on the machine learning model to figure out it needs to stay away to avoid that crash. You have local resource access. You can even do protocol conversion if you're not talking over standard protocols like MQTT. Over-the-air updates is also supported, so you can manage and update your devices from time to time over the air from the cloud. And finally, if it's a microcontroller device running a FreeRTOS, it can also talk to a Greengrass appliance. So now you understand about some of the features of Greengrass. Let's talk about few major components. The first one is Greengrass Core. This is like the lifeline of Greengrass. It is a runtime that is responsible for Lambda execution, messaging, device shadow, ML inferencing, and everything else that I just talked about. This software is designed to run on devices with at least 1 GHz of compute, 128 MB of RAM on either ARM or x86 architecture. And it runs on different flavors of Linux like Ubuntu, Raspbian, Amazon Linux. So Greengrass again is a software that can run on devices ranging from a Raspberry Pi to a server-level appliance to a connected car. The next component is a Greengrass group. So now you have all these devices, you need to group them in an organized way. That's what Greengrass group does for you. It's a set of cores and other devices configured to communicate with one another. In a group, you will add all these devices like your cars, in this case, your Lambda functions, your machine learning models, and routing rules, aka subscription rules, that you deploy them to the edge devices for them to work in an offline mode. The third component is IoT device SDK. So any edge device now that need to interact with the Greengrass core via the local network can use the device SDK or even a FreeRTOS SDK. So back to our example, let's see how the rubber meets the road, right? A connected car will have the Greengrass core running as a gateway. A Greengrass group will act as a container for all the different equipments within the car, like the infotainment system, the wiper controls, the airbag units, etc. And it will leverage IoT device SDKs or the FreeRTOS SDKs to talk to each other through Greengrass. And now they're talking to each other. The data can be collected and processed locally for certain use cases like crash or going to crash. And it can also be sent to the cloud through Greengrass for other use cases like analyzing the road conditions in that location or building machine learning models, tuning the models. So, opportunities are endless. With that, I will let you guys go, get your hands dirty, as that will help you to understand these concepts much, much better. Have fun. See you on the other side. What's up, builders? Hope you are enjoying the exercises so far. Up until now, your car things were connecting directly with the AWS IoT core service. But we told you those car things need to communicate on a local network, like on the roads, to avoid the round-trip latency to the cloud for crash-like situations. Remember? And that's where a service like AWS IoT Greengrass can help. So, how do you build this? If you remember the first exercise, yeah, that's a long time ago, but if you still remember, you created 2 cars to send telemetry data directly to AWS IoT Core. Well, this time, instead of that, car things will send data to a Greengrass running locally over the MQTT protocol. You will continue to use Cloud9 as your working environment. So you will start with installing, configuring, and starting the Greengrass core. Did you notice? In this case, Greengrass core will be running in the same environment as car 1 and car 2. But in real world, they would normally be separate. We did it to make the exercise simpler for you. And the code for the cars will use something called Greengrass Discovery API to communicate to other devices or to the Greengrass core locally. So now you have set up your cars. How can you do local processing with the Greengrass core? That's where you deploy a Lambda function at the edge to republish the data back to the cloud. In real cases, you might add more complex logic. Wait. Are you thinking what I'm thinking? How will all these cars and Greengrass and Lambda work together? That's what we refer to as creating subscriptions to connect the dots and orchestrate the workflow at the edge. So once you are done with all this Greengrass setup and configuring the cars and configuring the Lambdas, you have to start your car engine again. And finally, using the MQTT client in the AWS IoT console, just like before, you will start viewing all the incoming messages, but this time it's coming through Greengrass. Loosen your belt when the ride is over to clean up your resources. Let's go, builders. Have fun.
Welcome to the final week of our class. Last week was busy with discussions about communications protocols, security, and computing at the edge. There was a lot covered, and I hope you were able to get through the hands-on exercises. In this, our final week, I will dive a bit deeper into computing at the edge with the AWS Deep Lens device. Neil is going to look at using AWS IoT analytics to easily collect, pre-process, enrich, store, and analyze IoT data at scale. You will get to do a final exercise where you will use the AWS IoT Analytics service with the application you have been building out over the past 4 weeks. Yes, you guessed it, there will be some course notes, and this week there will also be a final exam. In the forum this week, like in the past, if you have questions or just want to help out your fellow students, feel free to jump in. If you have any thoughts about the class, suggestions, critiques, or compliments, we are listening. So please feel free to use the forums for that as well. I'll check in with you again at the end of this week. But now it's my turn to talk to you about AWS Deep Lens. Enjoy this, our final week. Last week, Bobby and Neil introduced computing at the edge and Greengrass. So now let's look at a use case for this. This is an AWS Deep Lens. It is a deep learning-enabled video camera optimized to run machine learning models and perform inference on the device. It can be integrated with Amazon SageMaker, our machine learning service that we covered in an earlier class. Information about machine learning and that course can be found in the course notes. Deep Lens has an Intel Atom processor, runs Ubuntu, and has a 4-megapixel camera that supports 1080p resolution. How does this relate to IoT? Deep Lens is also a Greengrass device. Why would you want to use something like this in an IoT environment? Say I need to know if there's a person crossing the road in front of our car. How would I do this? Well, I could set up a streaming video camera and have someone monitor the video. That might work if the camera was mounted on the side of the road or maybe even in the car, and I had a bunch of people to monitor the video feed. I can even improve upon this by using machine learning instead of humans in the central location to monitor the video feed, report back people sightings, and take action. But a video feed is very bandwidth intensive and therefore expensive. What if I could instead just do that with analysis at the edge? With a deep lens, I could do that ML processing and get my results right at the collection point. I would only need to send back a label. This appears to be a person, or this appears to be a box, and so on. The bandwidth required to do this is significantly less. I can even mount a device with these capabilities in my car and using Greengrass process the data locally and pass it back to my IoT core, just the data needed. Enough talk. Let me show you how it works. I've already registered my Deep Lens device. I'm going to go into the AWS console, go to Deep Lens, and you'll see I have a device here called AG Deep Lens. If I were to register a new device, I would click on Register Device, give the device a name. I would have to define permissions for this device and download a certificate. This certificate that I download, I will then upload to the device when I connect to it. As Bobby mentioned in our discussion about security, the Deep Lens uses certificate-based authentication. Deep Lens is also Wi-Fi enabled. I connect to the Wi-Fi network on the device itself. The network name is on the bottom, along with a network password. Once connected, I will set a network name on the device of a public Wi-Fi network or my corporate Wi-Fi network that I want to have this device hooked up to. I will also upload the certificate that I had previously downloaded to it. When done, my device will then be connected to that public network. I then also need to make sure that my laptop, my device, is actually connected to a public network as well. It doesn't have to be the same network. Once complete and the Deep Lens is online, I'll be able to see it in the console. So if I go back to the Deep Lens console and look at devices, I can see that my device here is registered and it is showing as online. I can now deploy a project to this Deep Lens. There are several sample projects available that come with Deep Lens, and I can say I want to create a new project. I can use the project template or create my own blank template here, or use templates that are available through the AWS Deep Lens community. I'm going to create a project using the object detection template here. It will select up to 20 popular items or objects. I say next. It will tell me what the project is. I have to give it a name, so we'll just call this edX demo. Detect up to 20 popular objects. It's going to tell me how this project works. It sees the objects. There's an inference Lambda function running on the Deep Lens device doing that object recognition. There will be an output video stream and a project stream. We'll see this in a few moments. I then hit create. My project is created called edX demo. I then want to deploy this project to my device. I go to my device, select the device, say deploy a project, edX demo, deploy to device. This will take a couple of minutes to deploy. Once I select it, review, deploy. Deployment is in process. This will take a few minutes. We'll be back when it is done. In a few minutes, the project has been deployed from AWS to your device. Once the status shows as online, I can look at the video stream from the camera. To do this, I'm going to go down in the project page here, look at project output, and I'll go view the video output. Select my browser, view the stream, and I will ask my assistant, Bobby, to come in here. And let's see, it thinks she's a person. And it's giving us a confidence score there of how much it thinks she's a person, about 75, 85%. That's great. Why don't you stay actually, Bobby? Because the next thing we're going to do is now go back to IoT. Okay, so we're looking at the data coming in, we've seen the video, but now we want to just stream those labels back to IoT. We don't want to actually stream all of that video. So to do that, I'm going to copy a topic that's been created in our Deep Lens project, open up my IoT console, paste in my topic, and subscribe to it. And now we see that it sees person, it sees chairs, it sees dining rooms, it sees monitors. So I can now, instead of streaming all that video back to my device, I can now just stream back these labels, and that number you're seeing next to it is a confidence indicator of how confident the model is that what it's seeing is what it is in a percentage. So again, this is significantly less data and allows me to limit what data is sent back to IoT Core. This could be useful to protect privacy or other confidential information. If you're interested in the Deep Lens device, there are links in the course material.
Hello builders, what's up? This is Neil again. Welcome back. In this video, you will learn about AWS IoT Analytics Service. If you're thinking, why does AWS need to build another service on top of 150 plus they have? You are at the right place at the right time. If you're familiar with any big data workflow, you might know that data needs to be collected, processed, stored, and consumed. The same holds for IoT workflows too, where you collect, process, store, and consume time series data. But there is a little difference. There are more challenges you have with IoT data. IoT data is not highly structured data because it may come from sensors attached to machinery that has intermittent network connections. The messages could be corrupted or have significant gaps or even false readings. Let's take an example. In the agriculture industry, farmers now can determine when to water their crops based on humidity sensor data. But the data might be noisy, as it's coming from a huge farm spanning acres with not great internet connectivity. To meaningfully use this information, the data needs to be enriched with other data like time, location, and that creates a challenge for application developers, you. Because you now have to create custom code to filter, process, transform, enrich this data. And it will take time for you to build, test, and maintain, which will add a processing cost to your applications. And that's when you asked if we can help in the most Amazonian way. If we can give you a service to quickly do all the steps without learning 15 other services that we have for analytics. And at AWS, we are obsessed about you. So we listened and we launched. AWS IoT Analytics is a fully managed service that helps you to quickly collect, pre-process, enrich, store, and analyze IoT device data at scale. And we have built different components to handle each of the steps within the service itself. The first component is called channel. It's your first point of data ingestion. It helps you collect your data from multiple sources. It could be an IoT core using a topic. It could be Kinesis, our real-time streaming service, or it could be just S3 or any custom source. The second component is called pipeline. It helps you create activities to filter your data, transform your data, enrich messages on the fly. Data store is a fully managed component for storing time series data because you have collected all the data, processed all this data, you need to store it somewhere. That's what data store does for you. And we have also added the capability to automatically partition the data for you to achieve faster performance. The next component is called a data set. Now you have all the data, you probably need to run some code on the data, you need to run SQL queries, and that's what data set does for you. It gives you an ANSI SQL capability to run queries on your data stored in the data store. Or you can bring your custom code as a Docker image to analyze your data as well. Then we have also added a built-in integration with machine learning notebooks, so you can take advantage of our machine learning platform, SageMaker. And we have built certain templates for most of the common IoT use cases, like predictive maintenance, forecasting, and many others. Let's stop here, and in the next video, we'll go into a deep dive. Thanks for listening. See you soon. Welcome back, builders. What's up? This is Neil again. As promised, I'm back to give you a deep dive into IoT Analytics service. And the best way to do this is to review some design patterns. So let's get started. The first design pattern that we are going to talk about is continuous data analytics. In this pattern, you might have devices like a refrigerator, a washing machine, a fitness tracker, or even a connected car from where you are collecting all the data, which is essentially your sensor payloads. And the data hits IoT Core, which is our managed service for handling trillions of transactions from IP-connected devices. Once it hits IoT Core, the data goes through a channel. If you remember, this is the first point of ingestion for your IoT data into IoT Analytics service. From the channel, the data goes through a pipeline. This is where you pre-process your data, you filter your data, you transform your data, and we give you built-in activities to make your life easier. Once the data is processed, the data needs to be persisted in a data store, which is quite similar to any database solution, but this data solution is optimized for time series data. And from the data store, the data can be processed on a schedule or in a contiguous manner. So you can schedule the data set to run at a minimum of 15 minutes to the highest of monthly. Or the other option is what we refer to as delta windows. Many times our customer says, you know what, I lose some messages in flight. If I have messages coming from 11:55 and my data set is scheduled to run at noon, I'm probably losing the last 5 minutes of my messages. How can you help us? And that's where we launched delta window capability with AWS IoT Analytics. So one of our manufacturing customer is using this pattern to monitor their machinery continuously. If the machinery goes down, it impacts their production. So they analyze all the sensor data coming from all their manufacturing equipments and proactively remediate issues or perform predictive maintenance. So now you understand about the continuous data analytics design pattern and one of its use case. Let's move on to the second design pattern. For on-demand analytics, you can collect data from your devices, again, which could be sensors, refrigerators, car, whatever it is, and analyze the data in an ad hoc fashion. So the way it will work, your devices will send the data similar to the last one to AWS IoT Core in an MQTT topic. IoT Core uses a rules engine to essentially publish the data to the channel, which is the first point of ingestion within the IoT Analytics service. From the channel, the data again goes through a pipeline of activities and gets persisted into a data store. And the data can be persisted infinitely, or you can select the retention period for the data. And now you have the data, you can run queries against the data. Because remember, data is the new oil. So where can you use it? A customer of ours is using this design pattern to analyze the sensor data from the smart buildings with different floors, different rooms, different locations, equipments in an ad hoc fashion to understand the utilization from time to time. The next design pattern is about extracting your data, transforming your data, and loading your data, also commonly referred to as ETL. If you want to perform ETL, you will use primarily the pipeline activities. So the data ingestion stays same from the things to the core to the channel. No changes over there. What changes is in the pipeline before it gets persisted to a data store. So we give you built-in activities. Like you can add attributes, you can remove attributes, you can calculate attributes using mathematical functions. You can enrich your data with device metadata or device state information like the device shadow that you have learned earlier. Or you can invoke a Lambda function if all of these activities does not suit your use case to perform any other transformations or data enrichment that you want to do. A great use case is from an automotive customer. Yeah, finally we're talking about a connected car use case here. So the cars are published the sensor payload with its location, and in the pipeline, the data is enriched with data from other external sources like weather.com and here maps using Lambda. So the driver could be alerted in real time if it's going to be rainy, if it's going to be foggy, or if there is a lot of congestion in few miles ahead. Sounds interesting, right? The next design pattern we are going to talk about is custom data analysis. So again, we are continuously listening to your feedback, and many of you told us that you are running some kind of IoT workload in your data center for a long time, and you don't want to reinvent the wheel. You'd like to bring the same code that you had in your on-premise environments and run in the cloud to take advantage of all the cloud-native capabilities. So if you have any existing code today for processing your data written in Java or Python or Octave or MATLAB, as long as you can Dockerize that, you can use that data with IoT analytics. And that's what we refer to as a container dataset. So just to be clear, SQL dataset is about running SQL queries on your data, versus containerized dataset is bringing your own code to analyze your data and generate business outcomes from there. One of our customers is a mining company. They're using this design pattern to increase the efficiency of its core trucks by maximizing the load for each of the trips. So what they do, they use custom code to identify any deviations from the target load and plan loading guidelines to improve operational efficiency. The next design pattern we are going to talk about is pretty common. It's visualization. You are getting all the data for doing something beneficial. You are not just doing it for fun, right? So you probably need a way to visualize the data to generate meaningful insights from the data. So you can visualize using several BI tools, but we provide you Amazon QuickSight, which is integrated with AWS IoT Analytics to help you do the same. And whether it's an industrial machinery, it's a connected car, it's a smart home, you probably need a single pane of glass view to view the state of all the devices you have so that you can reason on top of the data to transform your business outcomes. The final design pattern that we are going to talk about is about a smart application. So we are surrounded by smart things, and we will have more and more in the future. So the flow looks pretty similar. You are getting all the data from all your devices, which is going through a channel and a pipeline and a data store and a data set, and finally you would like to do machine learning on top of the data. So part of AWS IoT Analytics, you can directly connect all your IoT data that is in your data set now, whether it's a SQL dataset or a batch dataset, to a Jupyter notebook hosted in SageMaker. And then you can build and train and execute models right from there. So you can imagine that IoT Analytics helps you with a plethora of use cases. One customer of ours, they deal with connected cargoes, and they are using device data to better predict when heating and cooling systems will fail to prevent shipment damage. Hope this information is useful to you and will help you to build your own solutions taking advantage of IoT Analytics. Stay tuned to get your hands dirty with this cool service in the upcoming exercise. Have fun, guys. What's up, builders? Hope you enjoyed all the sessions so far. It's sad that this is your last exercise, but I'm very proud with what you have achieved till date. Incredible job. As you know, it had been our mission to help you with the tools and the processes for you to know the state of all your things and to be able to reason on top of the data coming from your things. So in this exercise, you will build a pipeline to collect, process, store, analyze all the telemetry data coming from the cars using AWS IoT Analytics service. You will also enrich the data based on the geo-coordinates of the car using a Lambda function. That will help you to determine if the weather in the location where the car is in is going to be bad. So you can notify the drivers to quickly get out of there. Once you have collected all this data through the pipeline into your data store, you will also create SQL queries to analyze the data for different use cases. That sounds like fun, right? And finally, Please do not forget to clean up all the resources based on the instructions provided. If you want to save the code, please do it prior to the cleanup. I hope you enjoyed working on the exercises as much as we enjoyed building them for you. Well, that was a fun ride, and hope you all enjoyed it as much as we did. Well done, builders. See you next time.
Thank you all for taking AWS IoT, developing and deploying an Internet of Things. We started the course looking at AWS IoT core services. We built out our project, interacting with AWS IoT rules and shadows, and using the SDKs to interact with our app. We dug in a bit to AWS IoT communications protocols and security. Then we looked at computing on the edge. This week, we finished the course with an introduction to AWS Deep Lens and AWS IoT Analytics. We hope that you enjoyed our time together. We certainly enjoyed creating this course for you. On behalf of Adam, Bobby, Neil, and Wes, I'd like to thank you for participating, and we look forward to visiting with you again in future classes.